in asymmetric crypto, if we take into account potential quantum attackers, then RSA and elliptic curves are going to be broken in polynomial time with Shor's algorithm. And so this has led to the massive amount of work on post-quantum cryptos that is now being on the way to standardization. In symmetric crypto, there hasn't been a result as striking as Shor's algorithm. We know of a few algorithms that are applicable. We know that quantum search, that is Grover's algorithm, can help us accelerate exhaustive search of the key. And we know of a few generic attacks that have quantum replacements. But this has led to the common saying that we maybe just need to tweak some parameters in order to protect all of symmetric crypto. Now, if you take a look at symmetric primitives, and especially at key probability attacks, which is going to be what we study today, let's say we have a block cipher, this family of permutations that are indexed by a key, K, and we want to recover the key of that. So that means, as an adversary, we have access to a few plaintext ciphertext pairs. We want to find the corresponding key. We know that there is a generic attack that is always applicable that basically defines the security of a cipher that is trying all the keys. And if we have an ideal cipher, then this is the only way that we can recover the key. But this classical exhaustive key search is simply an upper bound, and there are many constructions, many idealized constructions of ciphers that admit different generic attacks. Now let's switch to the quantum setting. Still have all the same symmetric constructions, and now we know that we have a generic key recovery that always applies. That's simply doing quantum search to recover the key. And similarly as before, this is simply an upper bound. We may consider constructions on which there are better generic attacks than that. And the problem is that, well, now we have to look at these quantum generic attacks if we want to know the exact amount of security that we can expect. So in this presentation, so this is going to be divided into two independent parts. Basically, the only thing that comes twice is quantum search, but quantum search is everywhere anyway. First, we're going to have a look at the event-also cipher, which is a very structured, very popular construction that appears everywhere. And second, we're going to have a look at multiple encryption. And this is going to be a pretext to have a look at quantum merging algorithms. Okay. So a little introduction to quantum computing. And this is a slide that I actually don't really need. So I can go into the details and say how we define the quantum computation model with the help of quantum circuits. So we have our computation state, which is made of qubits instead of bits. A state made of n qubits is represented with 2 to the n complex numbers, which are coined amplitudes. And this is a lot of information, but actually only a small, like almost none of it is immediately accessible to us, because the only way to access information on the system is to measure it. When you measure it, it becomes a classical system. So basically, quantum computation is different from classical computation, as it's some kind of probabilistic computation where the probabilities are complex numbers, so they can interfere destructively. And basically, none of this is needed for this presentation because we'll just be using black boxes, which especially for asymptotic algorithm is perfectly fine. We can compose them as we compose classical algorithms. In particular, the main, perhaps the most well-known, or at least one of the mostly used quantum algorithms is quantum search. It's a whole framework that basically translates everything that is an exhaustive and unstructured search problem into a quantum algorithm to do the same task. And what we mean usually by a search problem is that we have a search space, which must be really simple. And we have a function that simply given an element of the search space tells us whether it's a good one or a bad one. We're looking for a good one, as always. And now, if we only have that, if we only have this search space, the ability to sample an element from it and the ability to tell if an element is good, then in the classical setting, we're basically stuck at repeating all the time, sampling an element and testing it. And we have to repeat this basically number of elements over number of good elements times, because this depends on the probability of sampling a good element, right? So that's it for classical exhaustive search. And in the quantum setting, the algorithm that is analogous to that is quantum search, also known as Grover's algorithm. And basically it's something that you can generalize to any probabilistic algorithm. Like you can have any probabilistic algorithm and you can accelerate it, making sure that you will sample a good output of it faster. And in this algorithm, you only have to make, so you still have to make this kind of search iterates, but this time you're sampling elements with a quantum algorithm. So you need a quantum algorithm to sample elements. I need a quantum algorithm to test if an element is good. If you have that, then you need only a square root of the classical number of iterates up to a constant factor. And that's it. So you can see why this is immediately applicable to the exhaustive search of the key, because sampling a key at random is very easy. And testing if a key is the right one means simply you're going to try to encrypt the few plaintext you have and try to see if they match the few ciphertext, corresponding ciphertext that you have. And so this is immediately applicable. This is why we can use quantum search to speed up the exhaustive key search. The second tool that we're going to be using is Simon's algorithm. Now, Simon's algorithm actually precedes Shor's algorithm. It has a very similar structure, but it has become very popular more recently because we're now using it in symmetric cryptanalysis. It solves the following problem. It's a hidden period problem, but with like a Boolean hidden period, where you have a function and the function has the same outputs on x and x XOR s for some period s. Now, if you want to solve this classically and you only have access to the function f as a black box, then this is going to require to find a collision of f, basically. And finding a collision of f means time to the number 2. With Simon's algorithm, we can do a lot better if we have quantum access to the function f. That means being able to query f inside a quantum algorithm. And in particular, if we're able to produce quantum states that are uniform superposition, so basically they contain all the input outputs of f. If we're able to produce such states, which we can do if we have access to f as a quantum black box, then we can sample random orthogonal vectors to the period. And if we're able to do that, then basically we have the period because we can solve linear system. So we only need a single query of this form to sample an orthogonal vector to S. And we repeat this expected n times, and that's it. So we have a polynomial time algorithm to solve this problem. Okay, now let's have a look at our first target, the even-Monceau Seyfo. So even-Monceau is a very simple construction. It's very nice. It's the simplest construction of a cipher from a public permutation. And it was proposed like 1997. It's also very nice because it has a very strong structure, and usually a strong algebraic structure is going to, well, can be helpful for quantum attacks. So we have this public permutation with a public description, and we add 2n bits of key. We XOR one of the keys before, we apply the permutation, and we XOR one of the keys after. There is a trivial key recovery on that, which simply means guessing one of the keys. The remaining is trivial, like it's going to be something XORed K2, so it's done. We can do the trivial key recovery in time to the two with Grover search. But there is a better classical attack. There are better classical attacks, that are based basically on finding a collision of that. So the first classical collision attack is simply remarking that if you take this cipher and if you XOR the public permutation to it, then you have a function that is periodic, and it basically contains the period K1. So we're still focusing on this key K1. We don't care about K2 anymore. Focusing on K1, we simply have to find a collision of this function, cipher XOR permutation, and it's going to yield K1 with high probability. So there is an attack in time 2 to the power 2, because it's a function on n bits, and in data 2 to the power 2, because each time we make a query to the function, we need to make a query to the cipher. That's basically, well, the first, that is the lowest, it's a matching bound, right? It's the lowest time we could expect to obtain if the permutation is drawn uniformly at random. There is a whole trade-off curve that we can obtain then, simply by making a difference between the queries that we make to the cipher part and the queries that we make to the permutation part. So we can say, for example, we can get rid of K2 by XORing the outputs with two values, x and x plus 1. And now we have two functions, one that contains queries to the cipher, let's say function h, and one that contains queries to permutation, say the function j. And if we find a collision between these two functions, then we can assume, and it will occur with high probability, that this collision occurred for a pair of values that was x and x plus k1. And so if we have a limited number of queries, we're going to use all of these queries to build a database that will contain many values of this function h. And then we're going to we're going to query the function j, because we can query it as we want. And we're going to look for a collision on this database, a value that already occurs there. And we're going to check afterwards that this yields indeed the right key. So the time that we need in the second step depends on the amount of data that we had in the first step. And this creates a time data trade-off curve. Data times time equals to the n. That is tight, because there is a proof that basically you can't do better if the permutation is drawn at random. And at each point of the curve, we use a memory of size t to store the database. And finally, this can also be done in a non-plain text way, which is even better, because here I'm actually writing this with the chosen plain text, where we have the choice of the queries we made to the cipher. Even if you don't have the choice, this is still valid. That is a classical attack. You can make this a quantum attack, as remarked by Kuakedo and Mori. And you can make this a quantum attack very easily just by using the quantum black box. So in the first step, as I said, we are collecting many values, many classical queries to E. And in the second step, looking for a collision on these queries. And the second step is simply a search. right, an exhaustive search among all the queries that we're making for some of them having a collision. So basically, we can take out this search step and replace it by Grover's algorithm. And instead of having to deliver the search iterate, where we have to repeat this search, we have a square root of that quantum search iterate, which contain quantum evaluations of P, but well, quantum evaluations of P means it's fine because P has a public description. And this is going to give a time data trade-off curve, data times time squared equals to 2 to the n. And similarly, as the classical attack, at each point of the curve, we need a memory of size t because we need to store this database of queries to E. Okay. There is another attack on event also that was proposed in the same paper, and that is actually perhaps the one of the most well-known. I more or less triggered, alongside some earlier results, it more or less triggered our interest in looking at symmetric primitives from the point of view of a quantum attacker. The attack is very simple because I already presented this periodic function that we can make out of it. If you take the cipher and if you XOR the public permutation, then you have basically K2 plus P of X plus P of X plus K1, which is a secret. And this is a periodic of period K1. It's invariant if you XOR K1 to the input. And so you have a function with a hidden period, and this hidden period is the secret of the cipher. So if you have quantum access to this function, you can break it with Simon's algorithm. And by quantum access, we are really meaning here if you're able to produce these particular queries that you need in Simon's algorithm. It's particular quantum states which contain all the inputs outputs. So a query. Yeah, so with that, you can break it. And the only issue, of course, is that, well, if it's an issue, that the query to F contains the query to the cipher. So we have broken the even non-source cipher, but we have broken it if we are allowed to consider it as the black box, the secret key black box, as a quantum component. So to put it inside a quantum algorithm, and to query it as a quantum algorithm. If that's the model we're in, if we allow this kind of queries, then this is broken in polynomial time. So of course, the attacks that are presented have two drawbacks. The first one is that the quantum collision attack has a nice trade-off curve that is similar to the classical one. That looks more or less tight also. The only problem is that, of course, at each point of the curve, you use a memory of size t. The memory you're using is especially annoying. It's like a powerful quantum memory model. So it's interesting to know what we can do without that. And of course, the superposition attack is very powerful, but it's a superposition attack, right? If we remove this quantum superposition access, then well, we just can't do that anymore. This is where I'm going to present an algorithm that basically achieves, well, the best of both worlds in that still managed to make use of Simon's algorithm. That is making use of this hidden structure. And if you see this from this collision attack perspective, it's as if you were able to run the collision attack, but without using a memory of size exponential. Okay, the only issue that in order to present this efficiently, I have to introduce another example, and that would be the FX construction. So FX is like Evan-Mansour, but with a keyed cipher inside. So instead of knowing the permutation, we have replaced it by a cipher with a new key K. And that means if you know the internal key K, then this is Evan-Mansour, and you can break it out. This is where Evan-Mansour. So there was an attack proposed on this construction by Leander and May, which was simply guess the internal key. And once you know it, run the attack on even Mansour. Of course, if the attack on even Mansour works, then you're going to see that. And so this was a good guess for the internal key. If the attack doesn't work, you're going to see that as well. And so this wasn't a good guess, and you try again. So by making the guess with quantum search now, there will be there will be to the size of the key over 2 Grover iterates. And for each Grover iterate, you only need to run Simon's algorithm. That is assuming, of course, that you have access to the cipher as a quantum black box. Okay. If you look at this problem that this attack is solving, it is the following. You have given a family of functions. You want to find the single one that is periodic, because there is one of them that is periodic, and you want to find it. And so in full generality, you're going to combine Grover search and Simon's algorithm for that. The specific case that we have here, it's not the full general case, because the family of functions has a very simple, has a very specific form. Each function that we're studying is always a sum of something that is independent of our guess, because it always contains the same queries to the cipher, the fx construction. It's always a sum of that and something that is only dependent of our guess, because we make the guess on the internal permutation, and that is our guess of the internal key, and it only intervenes in this part. If we have a look at how we run the fx attack, and that would be perhaps the most technical part on quantum algorithms of this presentation. Grover's algorithm has all these iterates, and at each iterate, we have basically, we have to run this test algorithm as a little black box. We are testing our current state. And then each time after testing, we have some additional quantum operations to apply. So let's have a look at the test black box itself. Each time we make the test, we run Simon's algorithm. And so we have our current guess z here. And we run Simon's algorithm with the function fz. So we must make the queries to the function. So we create these query states here. With these states, we can run Simon's algorithm, detect the period, or detect that there is no period. And once we're done, we destroy the states, because we have to go to the next iteration. And to go to the next iteration, you must basically destroy all the junk that you obtain from this from the current computations. And once we get to the next iteration, we create the query states again for a new guess z, because z is varying. And we're in Simon's algorithm, we destroy them again. We create the query states again, etc., etc. Which means that at each iterate, we are creating a query to fz by querying f, querying jz. And we're always making queries to this function f, although it doesn't change at all. And it's a shame, because actually we could do better than that by reducing the query to f. So if we reduce the query to f, it looks different, because now we're going to set up the algorithm by simply making queries to f and keeping them alongside. And now each time we need to test a new guess of the function of the internal permutation in our case, we're simply having a look at the queries to f that are here in our memory, creating the states we need for Simon's algorithm, running Simon's algorithm, and then reverting the states back to query to f. And we're using these additional states in order to not have to remake the queries to f at each iterate. We only have to make the queries to jz, something that is only dependent on our guess anyway. So instead of making n times the number of iterates queries to the cipher, to the FX construction, we make only n queries. We make the queries once, and afterwards, all the Grover search is about finding a good guess. How does that change things for the even-monthsful cipher, which was my advertised target? Well, it doesn't change anything if we think of, well, the fact that Simon's algorithm needs queries that contain all the inputs outputs. If we want to produce such queries with only classical information, then we need basically the whole codebook, and that's not an attack anymore. But still, we can have a look at this construction, and we can look at it as an FX construction. If we stretch things a bit, we're going to say that we're only interested in we cut the key K1, so we're still only interested in K1, to cut it in two. And now there is part of K1 on which we're going to make well, to put the input to arbitrary zeros. And so we're going to say that this is a key that directly goes into the permutation. So it's as if we had a keyed function here in the middle. And now there is a key K1 that is smaller, and an actual input that is smaller. So we can make, we can create the whole codebook of this. And we can guess the internal key K1. So there is an attack on this now. And it looks like the attack on FX, because first we're going to produce the queries that contain the whole codebook, but the reduced codebook of this cipher. And next, we're going to search for the internal key K1. And while we're at it, we don't need to redo the queries. So we can afford to have this very costly step in which we simply query the whole codebook, reduced codebook, and put it in quantum states. And so we get to a time data trade-off curve that is the same as before, data times t squared equals 2 to the n. Something very different, though, is the memory usage. If you look at the classical data, you have time equals 2 to the n over t. The quantum data trade-off basically gives you a square root speedup on that. The square root speedup comes from quantum search. There is something that doesn't come from quantum search. And the fact that instead of using a memory size d at each point of the curve, we end up using a polynomial memory all the time, because the only thing we need to store is a quantum state, and the quantum state is very small in that case. So we're really using the algebraic structure of the cipher. And this is an attack that you can apply, like it applies on actual primitives. So there has now been some actual estimations and gate counts of attacks done by Xavier and Sam in this paper that I'm citing here. Okay, that was our example in even-monthsful. And now I'm getting to the second part of this presentation, studying multiple encryption. Things are going to be very different because we're not using Simon's algorithm anymore, so we don't have this algebraic structure that we use. It's going to be how to solve meet-in-the-middle problems in the best way possible, given quantum algorithms. So multiple encryption is a very simple primitive where we just say, well, in order to increase the security of a cipher, I'm just going to compose multiple ciphers with independent secret keys. And so I'm going to assume that the key material is always of n bits. So we have independent ciphers with keys of n over r bits if we make all of them. And so recovering the key means we have a few plaintext ciphertext pairs enough to discriminate the right key. I want to find this sequence of key K1 to KR that maps the plaintext to the ciphertext. The classical time complexity gets to the n over 2 using a meet-in-the-middle approach that we're going to see later. This problem is connected to K-list problem. And what I mean by K-list problem is, for example, this a K XOR problem with a single solution, where the input, so it's well, nothing to do with multiple encryption. You have lists of random values that you can compose, so 8-bin strings that we can sum with bitwise additions. And we're looking for a K tuple in these lists that sums to 0. So why these problems are connected? Actually, it's because they belong to a larger class of problems, which is by composite search. It was defined by Dino, Dunkelman, Keller, and Shamir. And it's basically a search problem in which you can compute and compute easily and check easily partial solutions to the problem. In the case of multiple encryption, partial solutions are going to be, for example, you can take sequences of keys, reduce sequences of keys. For example, you can take all the keys K1 and K2 that map some X to some Y. And then you can take keys K3 and K4 that maps Y to another value, and so on. In the case of sums like this, you can take smaller sums that have some prefix, that take some prefix condition, and you can keep this prefix condition alongside if you take bigger sums of it. Okay. That wasn't clear at all, so I'm going to give the idea of what happens for these K-list problems, but always in connection with the multiple encryption setting. When we try to solve a K-list problem like this, so we have these initial lists, and we're looking for elements that sum to 0. The basic building block is a merging algorithm, which would say that if we have two lists that contain bit strings, it is very easy to produce a list of pairs of elements that contains sums which have some partial prefix condition. If the prefix condition is a full prefix condition, that simply means finding a collision between the lists. Very easy. If it's a partial prefix condition, that simply means we're going to go through both lists at the same time, and we're going to find all these partial collisions. If the lists are sorted, the output list is going to be sorted as well, and the complexity is simply the size of the biggest list, either the input or the output that is involved. So the algorithm is as simple. It only requires to read and to write, but there is nothing more to it. So this is a very simple example of merging the meet in the middle attack. Well, you only have two lists. If you only have two lists and you're expecting a single 2 XOR, like a 2 XOR, a XOR of two elements that sum to 0, it's simply two equal elements. So this is simply like looking for a collision between the lists L1 and L2. This same situation for 2 encryption, it simply means we're looking for a K1 and a K2 such that K1 maps the plain text to some values, and K2 maps the ciphertext backwards to the same values. So this is simply a standard meet in the middle problem. Classically, both of these, so the K-list, 2-list variant, and the 2 encryption variant, have time and memory to the number 2. And quantumly, there is an algorithm to solve that. Also both variants that runs in time to the number 3. That is Bainey's quantum work. But of course, what's interesting is to increase the number of lists and to see what happens. So if you have 4 lists now, or alternatively, if we have 4 keys, So in the 4 list problem, we now have 4 lists of size to the number 4, and we're looking for inputs in each of these who sum to 0. In the 4 encryption problem, we're looking for 4 keys who map 4 plain text to 4 ciphertext. We can solve this with the same meet in the middle approach as before. But well, that simply means we're going to take all the sums, so merge, but with no condition at all. We take all the sums of pair or list, we'll take all the sums of the other pair, and then we look for a collision. And in the 4 encryption setting, this means we take all the possible pair of keys, K1, K2, all the possible pair of keys, K3, K4, and we look if there is a match between how they map the plain text and the ciphertext backwards. But you can do better than that with an idea that was introduced by Schrottenloher and Shamir. As a 4-list algorithm, and we're going to see later how it turns out as a 4 encryption algorithm. But as a 4-list algorithm, it is very simple. It's simply going to take an arbitrary prefix, and instead of computing the whole product of sums between L1 and L2, you're taking all the sums which start with this arbitrary prefix of n over 4 bits. And this is a list which is of size 2 to the number 4, approximately. And same for the other side. And next, you're looking for a collision between them. But of course, if you didn't choose the right prefix s, this collision doesn't happen. It only happens when s is the right prefix. There are 2 to the n over 4 choices, and you have to repeat that for all of them. But this means that for all of these 2 to the n over 4 choices, you have basically 2 to the n over 4 computations to make. And so the total time is still the same as before. But the memory is reduced because all of this, instead of being a large meet in the middle problem, becomes a little meet in the middle problem between 2 lists of size 2 to the n over 4. In general, you can apply this idea of selecting arbitrary prefixes and taking all the possible values of these prefixes, and for each possible value, merging your list according to these constraints. In the classical setting, this improves the memory complexity. In the quantum setting, this improves the time complexity, in addition to the memory. And this is something that is completely quantum specific. There are a few results that we can obtain by using this technique. And I'm not going to enter the details, just giving results. And next time, well, the only specific algorithm that I'm going to present is actually the algorithm for 4 encryption that we're going to see. But in general, for any k, there is like an optimization problem of how you're going to choose your prefixes and how you're going to merge and to do these loops on possible prefixes or choices of your prefixes. And this problem becomes basically, well, if you're only using quantum search as a black box, it becomes basically a linear optimization problem with some integer variables, because ultimately we are having initial lists of size 2 to the number k, which is why it has a time complexity that depends on some, well, on this formula basically. So when you cut the problem into, when you cut the search space into k parts and k goes to infinity, then the complexity goes to the 0.3 n. This was the results that we had last year in Eurocrypt. And I'm also advertising the fact that the paper was incorrectly referenced by Springer with the wrong title, so now it should be corrected. So this was results of last year. Actually, by studying this into a bit more detail and changing some constraints and how we write the algorithms, can obtain something a bit better. Turns out that problem seems to converge rather towards 2/7. So there are key encryption algorithms that, well, depending on how depending on the value of k, go to this complexity to the 2n/7. That is when the key material is always of size n, right? And it turns out that actually you can do a little better than that. But it's still going towards 2/7. This is slide 41, by the way, the one that nobody has seen before. This is because some additional optimizations. But so this curve means that there are quantum algorithms solving k encryption with k encryption or encryption with R keys of size n/r bits that reach these complexity exponents. Complexity is always exponential in n for each value of R. I'm going to take the example of for encryption to see a bit what happens. It is actually disappointingly simple. It starts like Chopin-Chamis algorithm, saying, hey, we're going to select a value for one of these intermediate. We're going to select an intermediate value at random, and it's going to work for one of them anyway. And for each of these values that we're selecting, we solve a smaller meet-in-the-middle problem. So we select a value S. So instead of having a prefix, we're now selecting a value for an intermediate state. So let's say for the encryption of one of the plaintexts, for the encryption of P1 in the middle, it should be equal to S, okay? And now the meet-in-the-middle problem that we're solving is, does there exist a pair K1, K2, which has this constraint, and a pair K3, K4, which has the also this constraint? Does there exist a match between them, as in a tuple of keys that sends all the plaintext to all the ciphertexts? In order to enumerate pairs K1, K2 that have this constraint, actually having pre-computed inner things, in particular having pre-computed all these mappings of P1 by the keys K1, it actually costs time 1 to get one of these pairs. So it's very easy. It's the same for pairs K3, K4. So this is like this meet-in-the-middle problem. In order to solve it, it is going to cost a time 2 to the power 4 if all the keys are of size 2 to the power 4. And so we recover the time complexity of Chopin-Chamis algorithm. In the quantum setting, as I said, it is a bit disappointingly easy. We have still to select a random S for this intermediate value that we're choosing. So we're doing a quantum search to select that. And it's going to be a bit faster. There is only one solution expected, by the way. There are 2 to the n/4 possibilities, as said, but only one solution. So basically 2 to the n/8 iterates. And then we have a meet-in-the-middle problem. But we have a black box for that, Ambéni's quantum walk, that was foreshadowed in one of the previous slides. And so S is of size n/4. So there's this quantum search here term. And for each value of S, we end up solving a meet-in-the-middle problem with lists of size 2 to the n/4. And so there is a meet-in-the-middle term here, n/4 times 2 over 3. And that's it. This gives something like the exponent 7n/24, which is the best we have for now for encryption, but which is also faster than 2 encryption with the same amount of key material, because 2 encryption was stuck at 2 to the power 3. And this is something that doesn't occur classically. Now, an interesting question, of course, would be by how much can we get faster than 2 encryption? And for now, all that I can say that this formula here simply is the best result we have. Okay, so I'm going to get to a conclusion, general conclusion and what I presented today. That there are many specific constructions in symmetric crypto that have like dedicated generic attacks, and the dedicated quantum attacks need also some investigation. We end up using all the quantum algorithms that are already well known, like Grover's algorithm, Simon's algorithm, maybe a few more exotic tools like quantum hooks, but it's still like the best tools we have. And what happens is that there are quantum, well, there are behaviors that maybe you wouldn't have expected from a purely classical point of view. For me, one of the prominent examples is in the offline Simon's algorithm, when you have this time-memory trade-off, time-data trade-off, and the memory that exists in the classical trade-off that simply slips away in the quantum trade. But also the example of merging and K encryption algorithm shows that there are time complexity gaps that do not exist classically, because the time complexity is still stuck at the same as to encryption, and that do exist quantumly. So this, like there are many different things to study yet. So with the offline Simon's algorithm, this is a more generic idea that you can apply to other settings. So we have been working on this with Paul Frixon, and there is an e-print now on that. I would like to mention also an interesting open question, of which I have absolutely no idea of the answer, whether there would be a quantum 3 encryption algorithm with a complexity better than the time that you get with 2 encryption. It would be 2 to the other 3. I don't know. Yeah, so that would be I don't know, an interesting thing to have a look at. And with that, I thank you for attention.